And next we're going to hear about the European approaches from Francis Westall, who is the leader of the exobiology group at CNRS in Orient.
Thank you. Good evening, good morning, good night, wherever you are. Thank you very much for the invitation to join this conference and to present. I just want to give you, say something first of all. I'm actually a South African-born geologist, and I'm now Director of Research at the CNRS in Orléans in France. But I have been working with ESA for the last 25 years. And I'm really grateful to Jim Green for having given the presentation he has, because my presentation is more from a scientific point of view, simply because I am a scientist. I'll speak a little bit about the ESA missions. So if I can get this moving, yes. I'm going to spend quite a bit of time about talking what I think we're looking for in terms of extraterrestrial life. Then I'll speak about ESA's program for Mars, ICE satellites, and also exoplanets, which overlaps a little bit with what Jim Green was talking about. So let's start with what we're looking for. Right, this is one of my favorite views of the Earth from space, looking down on the African continent. And we have seen various versions of this, but our Earth today has incredible variety of diversity of species, etc. Just about every single habitable location on the Earth is inhabited, including the crust. We even have technologically advanced species. I won't talk about intelligence, but just technological advancement. But in terms of extraterrestrial life, what could we expect to find? So I'm going to go back a little bit to the talks yesterday, how things started and what we might be finding, going on to Martin Rees's talk. So the most primitive form of life, according to my colleagues who are prebiotic chemists, say that the most primitive form of life is a living system in a mineral context, encasing. And Bill Martin talked about this yesterday. Then we have something called a protocell, which is a membrane encased collection of molecules, information transferring molecules, and molecules for taking on metabolic processes. And Barbara Sherwood-Lala was speaking about chemotrophs yesterday, specifically chemolithotrophs, very primitive organisms. These are the most primitive cells that we know of that are on the Earth today, chemotrophs and chemolithotrophs. And then we have the more well-defined phototrophic microbial mats. Today, most phototrophic microbial mats are, they comprise a wide variety of microbial communities, but one of their salient points is the production of oxygen by cyanobacteria. But way back when, let's say about 3.5 billion years ago, the phototrophic mats were anoxygenic. There's no oxygen production. And then, of course, come the eukaryotes with all kinds of varieties of organisms. So which of these can we expect? I think a lot of it depends on the habitable environment. And what I mean by habitable environment is what kind of a habitable environment, how long it was there for, what its continuity was. And this has an effect on the emergence of life and on continued flourishing life and even dormant life. So coming back to the talks yesterday, in terms of the emergence of life, if we're looking at the emergence of life on exposed land surfaces, and this is what Steve Benner was talking about, there are quite a number of hypotheses looking at various aspects of the emergence of life on land. Steve Benner spoke about reducing atmospheres in contact with reducing rocks or mantle rocks. John Sutherland's group is also looking at life on land. David Dame and David Diemer looking at the emergence of life in hot springs, and a group at ELSI in Tokyo looking at the emergence of life in concentrated concentrations of fueled by radioactive activity on land. Whatever, well, one can have various debates about these hypotheses, but if any of them is correct, it means that in order for life to appear, you need a landlocked world with lakes or with seas. And we can take, for example, Mars, early Mars, as Jim Green was talking about, or exoplanets. But it also means that life could not have appeared on ocean worlds. So any of our missions to search for life on the icy satellites of Jupiter or Saturn are doomed to failure. But what about the emergence of life in white smokers, as Bill Martin was talking about? This is an image of a white smoker off ridge from the North Atlantic, and this is the original image from Mike Russell and I think it's John Hall. No, it was Alan Hall in 1997, where they hypothesized about life emerging in such an environment, in plate tectonic environments. Now, they are hypothesizing plate tectonics. We need to keep in mind that on the early Earth, there's still quite a lot of debate, but plate tectonics, as we know it today, didn't exist and won't have existed on other planets. And this is Bill Martin's nice diagram that he showed yesterday of life, the influence of the hot reduced alkaline fluids coming through the chimneys, these white smoker chimneys, and eventually leading to life. So what does this mean? Well, if we're looking at ocean planets such as Europa or Enceladus, or even we could even consider the early Earth as an ocean planet because there was very little land mass. Maybe early Venus. Mars had some water, but no plate tectonics. The isosatellites, exoplanets. But again, you know, these are all hypotheses. We don't know yet how life appeared, and the scenario for the appearance of life has a great influence on where we might expect life to appear. Now, there's a variation on the hydrothermal theme, and this is one that I suggested a number of years ago, published in Astrobiology in 2015 and 2018. And this is the emergence of life in sediments associated with hydrothermal environments. We have here, I pulled these images from the web, and you can see hydrothermal fluids just trickling through, passing through sediments on the sea floor. And I think these environments were probably pretty important as well. And these environments were either in the deeper sea. This is a sketch showing sediments on top of basalt lava in the early ocean, shallow water basins, either at all water depths, including the beach. And this is another sketch showing these hydrothermal fluids passing through reactive sediments, minerals in the sediments, provoking interesting prebiotic chemistry. So if this scenario is correct, then life could have emerged in landlocked planets with seas, lakes, etc. We can also consider impact basins, large impact basins with a lot of hydrothermal activity and filled with water, lakes. And in this case, possibly, this could have, at least not the impacts, but the hydrothermal sediments would have been common also on ocean planets. So there's quite a variety. But the important thing is, well, we need to think of the emergence of life in terms of time and space. We have absolutely no idea how long it took for life to emerge. We think it was a very rapid process. Maybe it was hundreds of years, thousands of years, up to a million or so years. For a body of water containing the ingredients of life, carbon molecules, nutrients, energy, and so on, you need a body of water several hundreds of kilometers in size. So this means that the whole planet doesn't need to be habitable for the emergence of life. And this is important, for example, with respect to Mars, but also that habitability can be patchy, and that different types of habitable conditions can occur at different times in different places. This is something that I call punctuated habitability. And punctuated habitability has an influence on the evolution of life. So if we take this to Mars and look at the evolution of possible evolution of life and fate of life on Mars through time. This is a sketch taken from a paper by Dave Desmarais that we have doctored with my colleague Frederic Fouché. We're looking at pre-Noachian era here when there was liquid water on Mars, and this is the situation today. So as Jim Green mentioned, there's a gradual degradation in the habitable conditions at the surface of the planet, and with possibility of the emergence of life and viable microbes at the surface of the planet early on. Maybe today, if there is still life on the planet, it will be in the subsurface, in certain aquifers in the subsurface, but at the surface, we'll be looking at the fossil traces of life. Again, the question of punctuated habitability. Here's an image that Jim showed of Mars in its youth, Mars today. But because of the lack of continuous habitability of the planet, there's really very little possibility for evolution. So what kinds of life form would we expect on a planet like Mars? Well, we could expect the situation where in the landing site where we land, because we have no idea what happened where we're landing, we could just have prebiotic molecules. Or we may be able to find traces of cellular life, such as chemotrophs. Chemotrophs are organisms that obtain their energy from oxidation of organic or inorganic sources. If you really want to stretch your imagination, possibly even phototrophs at the surface, phototrophs obtaining their energy from the sunlight. I personally don't think that this is a very viable situation, but we don't know. And this is at the surface. Today, if there is life on the planet, it's in the subsurface, and it will therefore be very primitive. It certainly won't be, of course, can't be phototrophs because of the lack of availability of sunlight, so chemotrophs. And what about the icy satellites? Well, again, same situation. The organisms will be primitive organisms. They will not be phototrophs. They will have to be, we will be looking for traces of chemotrophic life forms. And well, with exoplanets, your imagination can lead you to wherever you want, possibly even mechanical or artificial life, as Martin Roos is talking about. So I want to concentrate on life before photosynthesis. And this is something that Barbara Sherwood-Lawler mentioned yesterday. I think that the life forms that appeared on early Earth before photosynthesis are the most likely life forms that we might find in the solar system. So we've seen these images before, but here below, I have some photographs of fossilized versions of these images of microbes. On the left, we have fossilized viruses. This is done by my PhD student, Francois Orange. If I saw fossilized viruses, I would not be able to recognize them. In the middle, we have a photograph of fossilized cells, probably hemolithotrophs, and these are from rocks nearly 3.5 billion years ago, old from Australia. This is my own work, and these interpretations, of course, are contested because the features, the signatures, are very difficult to identify. But in terms of the biosignatures, and this comes back to Jim Green's publication with his NASA colleagues on biosignatures, and it leads forward also into the talk by Heather Graham on the the agnostic biosignatures. But just briefly, I will class the biosignatures into the physical structures of microorganisms, cells, colonies, biofilms, etc. The organic cell components, and these will be the carbon molecules degraded to kerogen, or cell metabolic activity, which can be manifested in the presence of essential elements, the Schnaps elements that Jim spoke about, also transition metals, isotopic fractionation, and gases such as methane that was also mentioned previously. So I want to go on now to speak about the European missions, the European Space Agency missions related to astrobiology and the search for life in the solar system and elsewhere. But I'm going to take a step back to 1996, when this paper came out, written by David McKay and his colleagues from the Johnson Space Center, on the possibility of traces of life in a meteorite, the Allen Hills meteorite. I actually had the temerity to contest the group's findings, and David McKay, in the greatness of his spirit, invited me to join the group to work with them as the devil's advocate. But anyway, that's another story. What I want to say is that this story leads into the European Space Agency's program for searching for life in the solar system and elsewhere, because in that same year, as a consequence of that publication, the European Space Agency asked my predecessor here in Orléans, André Braque, and some other colleagues to get together a group of people to look at the possibility of an ideal mission to Mars to search for traces of life. And this ESA special publication is the result of this work, of the working group at the end of the 1990s. And I also wrote a paper on our work in 2000 in Planetary Space Science. So the ExoMars program, which constitutes, which comprises the trace gas orbiter, the Schiaparelli lander, and the Rosalind Franklin rover, is the direct consequence of our work at the end of the 1990s. The rover still has to leave, and I realized that people wanting to work in this field need to start young, at least younger than myself. Anyway, Jim has already spoken about methane on Mars and the possible sources, either microbial or geological, through serpentinization alteration of mantle rocks through serpentinization reactions to produce methane. But the trace gas, as Jim said, the SAM instrument on the Curiosity rover has found some small but significant traces of methane in Gale Crater. The trace gas orbiter is studying the chemistry and the physical and chemical characteristics of the atmosphere of Mars, and specifically looking for methane in the atmosphere. Well, frankly, methane, that trace gas orbiter hasn't really found any trace of methane. Well, just a few tens of parts per trillion measured using a couple of the instruments. And this is work that was published by Oleg Koroblev and his colleagues in 2019. So although, the trace gas orbiter actually cannot reach the surface of Mars, can only analyze the atmosphere down to about 5 kilometers, whereas the Curiosity rover in Gale crater is analyzing at the surface. So there's probably a discord just due to the different methods of analyses here. Coming back to the ExoMars rover, the Rosalind Franklin rover, named after the visionary scientist who discovered the double helix structure of DNA together with her male colleagues. So the ExoMars rover is a, the project, the ExoMars project, actually call it the bathtub because of its shape. It's very inelegant, but hopefully it's very workable. It has a number of instruments. I'll speak about the instruments in a while, but the salient point about the ExoMars rover is a drill to go down to 2 meters, which I'll tell you about. So there are a couple of papers on the mission. Hochschulwaage, there's a whole series of volume of the Astrobiology journal on the ExoMars mission with an overview chapter by Hochschulwaage and all of us, and also a recent paper on biosignatures for Mars by myself and my colleagues. So as with the NASA rovers, the ExoMars rover attempts to be a geologist in the field with analytical instruments. And I have a little insert here of the microscope, the close-up imager, because I'm co-PI on that imager. So the instrument, the rover is equipped with a wide range of instruments for observing and for analyzing. The Raman and the infrared spectrometers will analyze the mineralogy of the samples taken from 2 meters depth, and also identify the presence of organic carbon. Also, the GCLMS and LDMS will analyze the carbon molecules. Jim has already spoken about the oxidation at the surface of Mars. Also, experimental work has shown that there's a wide variety of radiation, gamma rays, radiation, ionizing radiation, background radiation that affects the subsurface of the Martian surface as well. So this is the reason why the ExoMars rover will try to drill down to 2 meters to take a sample from 2 meters that has not been affected by oxidizing conditions, radiation, and so on, so that we have a better chance of analyzing the organic molecules. The mission, the ExoMars rover will land in Oxyplanum, which is close to where we think there was a northern ocean. It's pretty flat, but quite safe for landing. This is because the mission doesn't have the point landing system that the NASA missions have. And here is an artist's illustration of the area that we might be landing in. But what are we looking for? I'm coming back to an image here. This is a colony of fossil cells, probably chemolithotrophic fossil cells containing carbon. So, but you'll notice that here's the scale bar, 10 microns. These cells are less than a micron in size. They're tiny. This is a detail, beautifully preserved, silicified, but tiny. So how are we going to find something like that? Well, probably the ExoMars rover will not be able to see the physical structures if there are any traces of fossil life there. We won't be able to measure any evidence for metabolic activity, but it will be able to analyze the carbon molecules and potentially gases such as methane. In terms of carbon molecules, we might be lucky and find, because the rate of degradation on Mars is a lot less than it is on our Earth, we might be able to find well-preserved molecules that are indicative of life, of active life, or even recently dead, dead life, such as fatty acids, etc., nucleotides. But this, for me, is wishful thinking, and Heather Graham will be talking about that as well. Most likely, if there was life in the landing area, we'd be finding the degraded remains of life. In this case, I'm showing molecules such as styrane and hopane that can be directly related back to biological molecules such as steroids or hopanoids. Most likely, we'll be looking for very, very degraded molecules such as thiophene, which can be produced a signature of life, but also an abiotic signature. So, as Jim was saying, we're looking at sample return, and ESA will be is participating in the Mars Sample Return Initiative, particularly with various parts of the mission. Now, very rapidly, the other missions from ESA related to astrobiology or with some kind of objective related to astrobiology. The first of these is the Jupiter Icy Moons Explorer, and it's called JUICE for short. I automatically think, in my brain's gone funny, I automatically think about Juicy Moons Explorer, but it's JUICE. But this is to explore the icy moons of Jupiter, to determine the structure, whether characterize the ocean layers, etc., as well as general investigation of these moons. Also of Europa, especially here with respect to any evidence of chemistry essential to life, as well as the presence of organic molecules. There's also the Plato mission, which is a planet finder mission, especially designed to find extrasolar planetary missions and to study any properties that might indicate that these planets would be similar to terrestrial planets in a habitable zone, using the techniques that Jim has been speaking about before. And as he mentioned, the James Webb Space Telescope is also partly an ESA mission. But I'm going to finish with just this one thought. Most likely, what we could anticipate finding in the solar system are traces of life before photosynthesis. And this means that we have huge challenges ahead. And I will end there. Thank you very much.